I'm the Eastern Regional Sales Manager for AMETEK Land, Maine to Florida and over to the Tennessee area. Today's presentation is on the proper selection of IR instruments. Because we have a various different backgrounds in the audience, I'm going to go over a little bit of the theory, then into the instruments, and then into applications. Now, of course, people can have innumerable type of applications. So at the end, obviously, we can take questions. This presentation will also be available if individuals would like it emailed over to them. So let's get underway. So anyways, we're going to be measuring IR, thermal radiation. So one of the questions right off the start, if people don't know it, well, what causes the emission of thermal radiation? Well, every element or compound out there is made up of atoms or molecules, and each structure has electrons which have vibrational and rotational movement. These movements result in acceleration of electrons, and these accelerating electrons result in electromagnetic emission. And that emission is known as thermal radiation. And it's important to keep in mind that it's somewhat of a surface effect. Over on the right here, this is a emittance spectrum. If you've ever looked at anything dealing with thermal radiation on the internet, you'll see hundreds of these. But by and large, they tend to be similar in nature. Every object that's emitting thermal energy will emit energy versus wavelength. And depending on the temperature of that object, it will emit different levels of energy. So it's good to keep in mind that all energy is emitted at certain wavelengths. Now, every object out there above 0 degrees Kelvin will emit thermal radiation. We can all feel it. If you put your hand next to especially a red hot object, you can feel thermal radiation. It tends to deal primarily in the range of about 0.75 to 15 microns. And the intensity of the energy emitted is actually to the fourth power. So if you take an object and you double the temperature, you will have a 16 times increase in the amount of thermal energy being radiated. Now, in the middle, as I just showed you the other graph, here is Planck's law of thermal radiation. And what this is basically showing that an object, let's call it a black body in this case, as the temperature increases, on the x-axis we have wavelengths, on the y-axis we have the energy emitted, and you can see there's a general trend of the temperature over into the upper left-hand corner. This graph just kind of gives you an illustration of what the physics are that we have to contend with when we're developing instruments for IR detection. And there's kind of 4 physical principles here that are shown in this graph. So with a growing object temperature, and you can see this temperature difference, there's an increase in the radiation power. And that's pretty obvious. If you go over to the Y scale, you can see that as the temperature goes up, more energy is being emitted. The second one, with growing object temperature, the maximum, look at the points, the maximum and the entire curves are shifting towards shorter wavelengths. So temperature goes up, the peaks, and the entire curve is shifting over to the left towards shorter wavelengths. Now, with growing object temperatures, the emission curve actually shifts into the visible spectrum, so we can basically see it with our eye as something turns red to orange to yellow to white hot. And if you actually look in the backwards directions here, as the temperatures comes down, you can see that at lower object temperatures, we're dealing with longer and longer wavelengths. So as the temperature comes down, if you want to be able to measure it with IR, you have to use longer wavelength instruments. Now, the area of interest for the IR spectrum tends to be about 1 to 15 microns. And in the industry, we kind of have that divvied up into like 3 general areas. Short wavelength is about 1 to 3. mid wavelength 3 to 5, long wavelength 5 to 15. Now, if you remember that graph on the previous slide, as you're moving towards hotter and hotter objects, the wavelength of where they're emitting energy is shorter and shorter. So you have, for very hot applications, you have to tend to use very short wavelength. Warmer, or let's say cooler type applications, I'm talking about 100 F and up, then you have to use long wavelength instrumentation in order to read. This here is just giving you, here's that graph from before, but this is just giving you an indication that as temperatures are growing, we're actually moving towards the visible spectrum, and that's clearly shown in this continuous pipe caster. Longer wavelengths at first, heading towards shorter wavelengths, shorter, all the way out to into the white hot area of the visible spectrum. So that previous curve was just, again, showing that as the temperatures increase, we're moving towards shorter and shorter wavelengths until we actually hit the visible spectrum. Now our eyes can see in the range of about 0.39 to 0.78 microns, but despite that, we're measuring IR in the 1 micron to 15 micron region. This was just to give you an idea of the visible aspects associated with temperatures. When you start getting around 1200 C, you're in the white hot area. Now, something we have to contend with, when you have a IR instrument, you're actually receiving the energy from the object. So we have to work within what we call atmospheric windows. Now, energy, as I've said a couple times, is being emitted at various wavelengths, and at some of those wavelengths, the energy can be absorbed by CO2 and water. And it's a little tough to see, but you can see at these wavelengths, you have a lot of areas where CO2 and H2O are actually absorbing the energy. Now, it may not be total absorption, but they are absorbing some. So for a thermal imager to work, to measure temperature, we have to look at the wavelengths where the energy is at least partially being transmitted through the atmosphere. So instruments' spectral response are designed for specific wavelengths where that energy is penetrating through. So in the entire worldwide IR industry, the most notable areas that pyrometers are built around are the spectral responses of like 1 micron, 1.6, 3.9, 4.3, 5, 1, and 8 to 15. So if you're looking at pyrometers, you'll tend to see that the spectral response tends to usually be in these areas. And it's just a necessity so that the instrument can actually see or pick up the thermal radiation. Now, what's the benefits of IR temperature measurement? Well, a good one is it's non-destructive and it's non-contact. We're measuring the thermal radiation, so we never touch it. It's a direct measurement of the object. We can literally pinpoint onto the object itself and measure the temperature. It's fast moving within milliseconds. It certainly has a quality improvement aspect to it since it's not non-contact. You can measure very small objects without withdrawing energy. If I have a very small object and I have to touch it with a thermocouple to get the temperature reading, obviously through conduction, you'll lose some of your heat and therefore you'll distort the temperature reading of very small objects. No problem with IR technology. We can also measure hot objects in very hot and aggressive environments. There are certain techniques to do that, and we can do that. And we can even measure in electromagnetic fields where you have induction and microwave type of furnaces. So there's a lot of benefits to IR. It can be a little more expensive than thermocouples, for example, but the technologies continue to improve and the benefits are clearly there. Now there's a couple real fundamental little equations that you have to deal with when you're dealing with IR. So let's take this scenario here where we have a red hot piece of steel sitting on a cold table. It has internal energy. It's actually resonating and transmitting that through thermal radiation. But that internal energy, some of it actually gets reflected at the boundary of the steel and air, and it's reflected back into the object, and some of it is emitted out. So just due to conservation of energy, if we look at this, we'd have to say that 100% of the energy is got to be equal to the reflected energy plus the emitted energy. These are percentages, reflection and the emittance. The internal energy here, it never radiates out. So if we just take our little equation and restate it, the emittance is equal to 1 minus the reflectance. So some of this energy never leaves, so the emittance will never be 1. It will always be less than 1 or 100%. So that was a hot object on a cool background. Now, if we move over to an object in a hotter background, let's say we take this steel object and we place it right here. The hotter background is actually radiating thermal energy onto that steel block. Some of it's being absorbed, some of it's being reflected, and some of it's being transmitted. So our equation is a little bit different. It's 100% that's equal to the absorption, the reflection, and the transmission. Now, in thermal equilibrium, the absorption will equal the emission, and most materials are solid, so you can't really see through them. Now, there are exceptions, glass, plastic, but usually the transmission is 0. So our equation here now simplifies to the same equation we had over here. 100% is equal to emissivity plus the reflection. Here's just something to keep in mind. It's the emitted radiation intensity that we saw on those graphs before at certain wavelengths, which is what we're measuring for the determination of the object temperature. So we're looking for temperature at a specific wavelength. So here's that hot object, internal reflection. Some of that energy is being emitted. The measurement of the emitted energy is how we determine the temperature. That emissivity or emitted energy will always have a value less than 1 because you have internal reflections. And if the emissivity value is not correct or is not known, errors can occur in your temperature measurement. So what exactly is emissivity? Well, emissivity is probably the most important factor for accuracy in the IR world. It has a definition to it, which is very simple. It's defined as the ratio of the emitted energy of a real object versus what the emitted energy would be for a black body object at the same temperature. In a black body, in an ideal world, E would be equal to 1. In the real world, E is never equal to 1. And how you can kind of, if you want to think about emissivity, let's take 2 pots of water, both of them at, let's say, 200 degrees. You have a stainless steel pot and you have a black enamel pot. If you would touch the stainless steel versus the black, obviously we all know intuitively the black would feel hotter, even though they're at the same temperatures than the stainless steel. What's the difference? The difference is emissivity. It's a surface effect, and it is different between a black enameled versus stainless steel. So a little more about this surface effect of emissivity. The easiest way may be able to just take an example, and we're going to assume we have a pyrometer in our hand that's looking at 3.9 micron wavelength. That's where we're measuring. If we take molten steel surface, we all know it's very smooth and it has very small, what I call nooks and crannies. Now, if we're, these are little imperfection, the little nooks and crannies. If we're using a 3.9 micron pyrometer, this wavelength is a lot larger than the little tiny nooks and crannies. So what happens, it's a reflection issue, but you will have more reflection since the wavelength is bigger than the nooks and crannies off of a smooth surface, and you will have less emission. So the emissivity of molten metals are very low versus the reflection is very high. Now let's just look at the slag surface. Well, it's the opposite. It's rough. It has very large nooks and crannies. So when we're still using the same pyrometer at 3.9 microns, this wavelength is smaller than the nooks and crannies. So the energy actually gets diffused in those little nooks and crannies. So we have less reflection and more emission, or emissivity is higher. So that's kind of what I mean by a surface effect. If it's very rough, it will tend to have high emissivity, low reflectivity. If it's very smooth like a mirror, you'll have very high reflection and low emissivity. Now, since emissivity can cause errors if it's the wrong value, pyrometers, which are designed by competing companies out there, they have what they call a certain detection. It's called the scale shape. And what it simply is, if we go back to one of our graphs from before, we had energy on the y-axis, in this case, temperature on the x-axis. This scale shape is the change in energy that we would see per degree increase in temperature. In other words, it's actually the slope. It's the change in y over the change in x. Shorter wavelength pyrometers have larger scale shapes. They have steeper slopes to them. So if we would have an error, a delta change in energy, if you take that error or that change in energy, dividing by a larger scale shape, it results in less error. Now, what all this means is simply the last bullet point here, that when you're using pyrometers, you want to tend to use the shortest wavelength when possible, because if there are errors, a shorter wavelength pyrometer will minimize the error. The right-hand graph here just shows the difference. If I have 4 different pyrometers all operating at different wavelengths, if I have a change in energy, the smallest error is associated with the shortest wavelength. So the 1 micron here, and you can see the worst pyrometer is a pyrometer operating at 8 to 14 microns because it has the smallest scale shape. So it has the largest error associated with it. Now, emissivity, I've stated here how important it is. Well, how do we know what it is? What is the value? Well, the good news is this technology has been around for many decades, so there are common tables with materials and their emissivities. In the field, the most notable way of determining emissivity is by using a thermocouple. You take a thermocouple, you take a reference temperature measurement on the object of interest, then you take the pyrometer and change the emissivity value until it equals the reference temperature. When you achieve the reference temperature, you now know what the emissivity of that object is. You can also do other things. There are special paints with known emissivities. Most of the time it's black, and it can have an emissivity of around 0.95. You can compare reference surfaces with known emissivities. You can determine by laboratory methods or experience, or you can even use a product that Land developed decades ago. It's called a gold cup. This gold cup is kind of a shroud. You touch it to a hot surface, the energy reflects off the gold, and the reflectivity begins to decrease with infinite reflections, and your emissivity gets driven towards 1. If your emissivity is 1, you almost have a perfect temperature measurement of whatever the object is you're looking for. In terms of angles, now whether this is a portable system or a fixed system, we typically are normal to the surface. Now it can be at an angle, but typically what you want to do is keep that pyrometer less than 50 degrees to normal. What this is showing here is the emissivity value. When you get out to, let's say, 40, 45 to 50, there's really no change in emissivity. And in this case, this would be an error that would occur in emissivity. After 50, you can see the emissivity falls off very quickly, and that would result in significant error. So applications come up, you want to keep the angle at 50 degrees or closer to normal. Another concern when you're dealing with applications are reflections. I had an initial slide up there showing a steel block, where that steel block was getting energy from a hotter background, and that energy is additive to the self-radiation from the object itself. Well, the same thing can occur with sunlight or different type of tungsten lamps. If I've got a pyrometer that's operating at 1 micron, the sun reflecting off of the surface can actually add to the amount of radiation detected by the pyrometer, thus giving an error. And so can lamps. So we've got to be careful when we're measuring inside a factory that we don't have, let's say, glass windows nearby where the sun can actually reflect onto the object. Tungsten type of lamps, we've got to be careful and take into consideration reflections. Over on the right, this is just showing whatever spectral response of an instrument we would use, let's say 1 micron or 1.6 or 2.4, 3.9, we can see that sunlight across the temperature range can result in errors. So this, I would say 70–80% of the time reflections are not a concern, but we do have applications, especially on like steel strip, galvanized strip, aluminum strip, where you have big targets and the reflections can sometimes be troublesome. Now, getting into the type of IR instruments. Well, there are basically 3 different types out there. One is a pyrometer, which I've used that word several times. We call it one-dimensional, but essentially it measures a fixed point. It's a single point measurement. So we call it 1D or one-dimensional. Then you have line scanners, which are sweeping across in a line taking measurements. Well, that is a 2-dimensional type of system. And then you have the thermal imager, which is kind of taking like a movie screen of the thermal aspects of whatever you're looking at. We call that 3-dimensional. Now keep in mind that all of these have detectors in them. All those detectors are measuring the intensity of the radiation. That intensity is then used in a lookup table to determine the temperature of the object. Now, this is a typical pyrometer. You have a camera body here, a hot target. You have some focusing objects. You have a mirror, and then you have a detector. Now, there are different type of pyrometers out there. You'll see this more and more if you're not schooled in this area, but you have single wavelength pyrometers. They're typically referred to as monopyrometers. They're detecting radiation at a single wavelength. You can have narrow band pyrometers, which detect within a narrow band. For example, let's say 3 to 5 microns. You can have ratio pyrometers that are using 2 or more different wavelengths. Let's say 2.0 versus 2.3. So those are ratio pyrometers. And you have fiber optic pyrometers. Now these can be both mono and ratio, but they have a fiber optic mechanism, a light pipe attached to the end with an optical head. These tend to be used in areas where it's a hostile environment and you need to put that little optical head close to the target, but put the pyrometer up to 30 feet away. Now the operating range of pyrometers is vast. Now, no one pyrometer can handle 120 to 5400 F, but when through different models, we can literally measure down to 120 F or all the way up to 5400 F. An issue that comes up a lot of times is the spot size. We're receiving energy off the target. Now, especially if you have a small target, it's important that you know what the spot size is. Now, using the field of view, which is printed on everyone's literature, it's pretty simple. If the field of view is 100 to 1, then at 100 inches setback or distance, the target is a 1-inch spot. Now, you usually have a minimum distance to maintain focus. Sometimes we get these applications where they want to measure, let's say, 1/8 of an inch wire. So we have to use close-up lens. You have to focus in maybe 4 inches back. So you can do that. You can look at very small objects. Now, it's important that when you're looking at the object, that the target, the object you're looking at, the target feels the spot size of the monopyrometer. If it's too small, it will read a lower temperature. Now, if the spot size is not completely filled, again, let's just say we're looking at an 1/8 of an inch diameter wire, it's very difficult to do that. Then to get an accurate reading, you may have to use what we call a ratio pyrometer. So in simplistic terms, what's a ratio pyrometer? It's a pyrometer that uses 2 detectors versus a single detector of a monopyrometer. Now, a ratio pyrometer, at times you'll see it on the internet. Companies call it 2-color, but they're the same thing. They measure the intensity of the target at 2 different wavelengths. Now, if the target is smaller than the spot size, as I just mentioned, like with a monopyrometer, if you feel the complete spot, no problem. But if you do not feel the complete spot size, you'll have an error. So that's where you shift over to ratio pyrometers, where if it's completely filled, that's no problem at all anyways. But if it's smaller than the field of view or the spot size, then a ratio pyrometer will still function properly. The reason is that when you use 2 detectors, the ratio remains the same even if the spot size is smaller than, if the target is smaller than the spot size. So a ratio pyrometer tends to be used when steam or dust are blocking the received signal, creating this condition. And despite a change in energy due to the blocking of particulate or steam or water, the ratio measurement is not affected. Now, the emissivity adjustment of the 2 detectors of a ratio pyrometer is known as the non-grayness ratio. I'm not going to go into that, but on a monopyrometer, you can adjust the emissivity. On a ratio pyrometer, you adjust the non-grayness ratio in order to improve the reading. Now, another type of pyrometer we have is called an algorithmic ratio pyrometer. Now, these are used in very difficult applications where you have low emissivity and where that emissivity is changing during the process. let's just take a galvanizing line from where it's wetted with zinc. As it proceeds downstream, it dries. So the surface conditions are changing. So it becomes the emissivity is changing. And despite having the ability to change non-grayness ratios, due to the changing effects of emissivity, we can't do it very well. So you have to use these algorithmic pyrometers, which automatically determine the correct emissivities or the non-grayness of the measured object in an algorithm, and they correct the temperature reading in real time. The algorithms are determined with significant field tests and data capture. When we design these, we have to go to aluminum plants or galvanizing plants and spend considerable amounts of time capturing data with pyrometers, noting temperatures, radiances, detector values, and in the end, we have to generate the algorithmic curves over the temperature range of interest, and that is then used to determine in real time the temperatures. So the two significant applications that we, as well as other competitors, are looking at are in the aluminum and galvanizing areas. Both those products, they're shiny. So they're shiny, and as I mentioned in one of the slides, if they're shiny, then they have high reflectivity, low emissivity. If you have a low emissivity, it's more and more difficult to read the thermal radiation being given off. Now, those were pyrometers. The 2D system is a line scanning thermal imager. Now, you can see our little sensor head over here. These are used in applications where the product is moving past the sensor head. Now, the design, it's simply kind of a rotating mirror internal here we call a scanner, which spins and it directs energy onto a single detector. Now, what this will do, it will take 1,000 samples due to the rotating scanner for each line, and hundreds of lines can be taken per second. So let's say 1,000 samples are taken per line, and we program it to run at 100 lines a second. We're literally taking 100,000 sample points per second. So the response time is very fast, 1 microsecond, and we're using all that data. We're generating what we call a detailed thermal map. So this map gets produced with all that temperature data within. Now, a typical installation of a scanner, it's sitting above your product of interest, whether this is steel or glass slabs or wood or all kind of things. We usually mount it perpendicular to the target, though it can be mounted off to the side and tilted. Let's say we rotate this clockwise 45 degrees. It can sit over here, but yet it's looking down onto the object of interest. The setback distance, this comes up a lot of times because the question is, what's the clearance? How high do we have to be? How low do we have to be? Well, typically it's pretty easy. We take, due to this being an 80-degree angle, the trigonometry works out that if you take the product width, you divide it by 1.68, that gives you the target distance back, or what we call the setback distance. Now this angle is 80 degrees, but it can be adjusted. So if somebody has to go up, let's say 15 foot up, we can adjust this angle so that we can at least view the maximum width of whatever product you're measuring the temperature off of. So the acquisition rates, again, are very high. They actually can be up to 150,000 samples per second. The spot size is around a ½ inch at a 45-inch setback distance. Let's just take a real world example. Let's take a cement kiln. Let's say it's 168 foot long. That equals 2,016 inches. We're taking 1,000 scans per line. So we're actually reading every 2 inches along that kiln. Now the setback distance, I made it convenient here, 168 foot long divided by 1.68 means this setback distance is equal to 100 foot. Our field of view is 100 to 1. So with this being set back 100 feet, the spot size is 1 foot in diameter. Now that might sound large, but again, keep in mind, we're taking readings every 2 inches. So every 2 inches, there's significant overlap in those samples. So we're grabbing significant data in the horizontal direction. And in this case, since we have a rotating kiln, depending on the speed of rotation, we're also taking line after line after line after line. So this is a very quick and effective way to gather temperature data across many different applications. This is probably our most versatile of all kind of thermal imagers. Operates in all kind of ways in the steel industry, cement, unique application like torpedo cars, low E glass, container glass, flat glass, conveyors for coal, biomass, anything being transported that could potentially combust, textiles, paper, wood products, plastics, the list goes on and on. So it's a very versatile way of determining temperatures. The third type of instrument out there are thermal imaging systems, and I call it TI for short. These are thermal imaging cameras, which tend to produce thermal images. So TI systems are used in applications where it's important to capture the thermal images and the video files. They tend to be designed around certain spectral responses. The detector industry tends to drive some of this, but the most notable wavelengths that thermal cameras operate on are 1, 3.9, and 8 to 15. And if you remember back, short wavelength, you want to use 1 micron. Mid wavelength, you want to use 3.9. Long wavelength, you want to use 8 to 15 spectral responses in the thermal imaging systems. Now they can measure, depending on the models, again, anywhere from 100 to maybe 3300 F. So we cover like glass melt tanks. We're number 1 in the world in that area, or close to it. They're about the hottest. They're up there around 3300 F. These are designed with focal plane array detectors, and the pixel count drives the resolution of the camera. And as we all know with our iPhones, high definition detectors are enabling high definition IR cameras. So we now have HD cameras up to 3 megabytes of pixel resolution. And just keep in mind, it might be 3 million pixels, but each pixel is operating like its own little single pyrometer. And it's notable here, that's why I put in this last bullet, the atmospheric conditions within a furnace can drive the use of a 1 versus a 3.9 micron system. I mentioned these cameras are kind of like CCTV cameras or movie cameras. They've got a horizontal field of view, vertical field of view, and an instantaneous field of view. They all tend to have similar aspect ratios, or they go by pixel counts. In this case, 1968 by 1476 pixels, that's somewhere around 3 million individual temperature measurements. So you get significant data out with thermal imaging cameras. Now the cameras can have different viewing angles, different fields of view. The instantaneous field of view is a single pixel size at a set distance. It kind of gives you an idea what the resolution is. Camera prices can swing anywhere from very affordable to high end, and these are also calibrated against black body calibrators. Now, in very small applications, you may have to be careful about the number of pixels that you can get a reading off of. We have cameras that can actually measure skin and body temperatures, In those cases, it's important that we at least get 3 pixels in order to get a proper reading. But when you're measuring large applications that just say glass melt tanks, cement kilns, reformers, you really don't need to worry about a minimal number of pixels. Now, thermal imaging systems can be standalone cameras. They capture images, video files across numerous applications, visible imagery coupled with hundreds of thousands of temperature measurements are desired. That's why you use these. They can be mounted external to furnaces or vessels. They can view large areas, let's say like flares or coal piles, biomass storage piles. We have some pretty unique applications out there where you have to look at large areas. You're looking for fires in some of these cases. They can be used to capture thermal maps of the hottest molten metals to the coolest aluminum strip. The next variety of thermal imaging system are the borescope cameras. Now, these are used in applications where the camera views inside the furnace or the vessel. It doesn't mean a standalone camera can't be mounted looking in, but these have borescopes on the end with an objective lens. They're used when you want to get significant detail within a furnace or vessel. The heart of the borescope system still remains the standalone camera that we just talked about, but they're put in an air and water cooled jacket for protection. Now, these conditions within furnaces can be harsh, and precautions must be made to extract the probes if you lose the air or the water cooling. And in those cases, you use what we call auto retract. These things detect excessive temperatures on the objective lens or the camera, and they'll pull the camera, the borescope, out of the furnace. Now, these can be fairly expensive, and there are Class 1 Div 2 versions available. Typically, hydrogen reformers, methanol, methane, they need C1D2, and we do, those are available out there. Now, application software, we have oodles of software out there running all of our pyrometers, line scanners, thermal imagers. The software in general, it should enable you the live video and image acquisition. We want pictures as well as video. We want to be able to archive them, play them back, and do analysis on it. You want to do profiling, trending, histograms, all ought to be available so you can do deep dives, so you can dig down into the data. Specific areas, or what we call regions of interest, need to be available to enable unique data capture, tracking, and alarming. It's a little tough to see, but there's a square here or a line. These are what we call regions of interest. You can drill down into specific areas of the entire thermal image that you're getting. Data logging, of course, that's important, can be manually or automatically engaged off of alarm activations, or you can just data log on a continuous basis. And you have to have I/O interface to the software, whether that's Ethernet modules or Modbus or other SDKs. There are other forms of communication for process control. Now, I think there's 3 unique applications I just thought I'd touch base on. The one is where you have a hotter background than a product. I mentioned this before. If we have a steel slab in a reheat furnace or tube wall in a reformer, it's emitting energy at its temperature, plus it's picking up reflected energy off the back wall of that reheat furnace or reformer. That is a source of air. So we have to take that in consideration. We can do that by using a second pyrometer or a thermocouple just to measure what the background temperature is, or you can use a second, or you can use the NIRB, a thermal imager, to not only look at the furnace, but to mark an area in the field of view as a background correction area. So either with pyrometers or thermal imagers, we can handle this kind of background, but it is unique. There's another unique application called a wedge measurement. Now, black body calibrators are used to calibrate pyrometers, scanners, thermal imagers. In a black body, in one of my first slides, basic equation, one is equal to the emissivity plus the reflection. Well, when you use a black body calibrator, inside there, you have infinite reflections. With each reflection, some of the energy is absorbed. So what's happening is the reflectivity is pushing towards a value of 0, and thus E, or the emissivity, is pushing towards a value of 1. So this same condition can be created between a strip and a roller. So if we have a strip and we have a roller, you can literally look into that wedge, and that wedge creates the same kind of condition as a black body does. You have infinite reflections. Those reflections move towards 0 because of the absorption of energy, and E, the emissivity, will move towards 1. So guess what? If your emissivity is basically 1 or very close to it, you don't have any air, so you have a very accurate temperature reading. The optimum angle, we figure that out, but it's typically about halfway of what this is based on a certain distance. And there's some math behind it, but we can tell what the angle needs to be. So this application is specific to strip temperature measurements, especially where strip is at a very low temperature. Low temperature means high reflectivity, low emissivity. So a wedge improves the emissivity by driving it towards 1. Okay, the last unique application is skin and body temperature. We all love COVID. COVID drove a large market for skin temperature measurement. It's a very challenging application, to be honest, and we use a small pixel array detector in order to determine that temperature. Now, your skin temperature is not your core body temperature, so you have to contend with ambient temperatures. If somebody walks in from the winter weather, their body temperature is not going to be 98.6 as soon as they walk through the door. So you have to contend for that. You do that using algorithms and offsets that will improve the accuracy. And if you really want accuracy, we did this with several thousand systems we sold during COVID. You have a black body calibrator literally within the field of view of the camera. So the camera always knows how accurate its electronics are because it's always looking at a stable black body. Okay, I think the last slide here, I didn't know whether to put this first or last, but I put it last. This is what we call kind of a IR capture questionnaire. If we have an application, these are some of the questions that I go down through, but I'll give you the question and then the reasoning behind it. But one of the questions, well, what's your process? Well, the issue is we need to know what kind of application we're dealing with. Is it metals, plastics, paper, whatever? Number 2, what's the material that the temperature will be measured from? Well, materials have different emissivities. I mentioned that. And the phase, are we liquid or solid, can be an issue. The customer, do you desire to have a single temperature measurement, like a pyrometer, or a line scanning thermal imager, or thermal imager in general? What do you prefer? Are there special conditions of the material of interest? Remember, the surface condition has a direct impact on the emissivity, so we need to know this. What's the temperature range? Well, that's a gimme because we have different pyrometers for different temperatures. How far away will the product be from the IR analyzer? Well, this brings into consideration the field of view, and the focusing distance might be considered. I had 5 projects come up in the last few months where they were all requiring close-up lenses. What's the objective of the temperature measurement? Sometimes we're just curious. What do you want to know the temperature for? This helps us make the decision for you. Is the size of the product very small? Well, this impacts whether you might need close-up lenses. What are the conditions around the measurement point? Dirty, clean? Remember atmospheric windows? Well, and also whether you'll have obscurance due to particulate, steam, or water. It can drive whether you need a mono or a ratio pyrometer. How hot's the ambient condition? Well, this is in general, we've got to be careful with regard to ambient temperature on the electronics. And how do you want to communicate? Some customers still want analog, some want digital, some want both, some want Modbus. Well, what's the most effective means of data capture for you and your process control? And finally, of course, is pricing critical? Of course, it's always an issue, but budgets can determine the overall solution, so that helps us along. All right. I don't know how long that took, but I do appreciate people staying involved there.